Okay, so I just wanted to do a couple of examples and focus more on the process rather than the actual, I guess, type of problem. And so we'll do one with friction, and then we'll do one with inclined planes. And in general, what we're going to be doing is the first thing that you would do is draw a force diagram. And then diagram, always. If it's kinematics, then draw your motion diagram as well. And then you want to identify whether there is acceleration or not. So ID acceleration. Is it 0 or what? Because if the acceleration is 0, then the net force is 0. And if there is acceleration, then that's equal to the net force over the mass. So Newton's first and Newton's second. So remember, work from first principles. There's also, you might have to use some definitions, like for friction, and then we would just substitute that in. So in general, what we do is we work, we have some stuff, and then as we go down, we start substituting. I don't know if that's spelled right. We start substituting and changing each side as we go down until we have a bunch of stuff that we know. And then we solve it with algebra. So let's do one with friction. Let's say we had a box that was sliding, or an object that was sliding across a surface. And let's say the initial velocity is 9 meters per second or something like that. There's no forces being applied, so it's like we pushed it and then we just let it go. And there's friction, so we have the coefficient of static friction and a coefficient of kinetic friction. So the static friction, maybe it's like 0.7 and the kinetic is 0.4. And so since it's in motion, we're going to be looking at the kinetic friction. So again, the first thing we're going to do is we're going to identify, or we're going to draw a force diagram for this. So here's my object. And then we have the force of gravity, which is pulling it down. This is the weight. And we always calculate the force of gravity as mg. And then we're going to have a normal force, which goes up. And then we're going to have friction working backwards. So the question might be like, how far does it take? Like, how far is it going to go until it stops? Something like that. Okay, so working with this, let's see so we drew the force diagram. The next step is, is there acceleration? So we have to look in the y and the x. So in the y direction, the acceleration is 0. So the acceleration in the y equals 0. In the x direction, we have a force. We have an unbalanced force, so there's going to be acceleration. So the acceleration in the x direction is going to be the net force over the mass. So now we can start substituting. So I have my first principle written down, and now I'm just going to start substituting. Because the acceleration is equal to 0, the net force is equal to 0 in the y direction. Now I change this, so I'm going to substitute in. So in the y, I have the normal force. We'll say up is positive. So the normal force minus the force of gravity is equal to 0. Now I'll go ahead and substitute for force of gravity, because that's equal to mg. So the normal force minus mg is equal to 0. So the normal force is equal to mg. So maybe this mass is, 4 kilograms. Then I can calculate the normal force. So that would be 4 times 9.8. So the normal is approximately, I'm just going to round, is approximately 40 newtons. Okay, you might be wondering, well, why do I need normal? Because that has nothing to do with how far it goes. Well, we may need it. And we will over here. So now we'll start substituting. So the acceleration in the x direction is the net force in the x direction, and the only force in the x direction is the kinetic friction divided by the mass. So the acceleration in the x direction, kinetic friction, I'm going to substitute the definition. That's the coefficient of kinetic friction times the normal force divided by the mass. So the acceleration in the x direction, well, I need to substitute for the normal force now. And the normal force is 40 newtons. But what I'm going to do is I'm going to put mg in there, because I'm going to do it algebraically. Because when you do it algebraically, you can see that the mass cancels. So the acceleration in the x is going to be the coefficient of kinetic friction times g. And there's my acceleration. So now I can use this with kinematics to figure out how far it goes. So now we're going to go over to kinematics. And I don't have the time, but I have an acceleration and I have an initial velocity. So we would use v squared is v naught squared plus 2a delta x. Now if it slides to a stop, then the final velocity is 0. V naught squared plus 2a delta x. So I would subtract this over. Negative 2a delta x equals v naught squared. And then we'll take the square root. But you might be thinking that it's going to be a square root of a negative, but it's not, because this acceleration is negative. Since it's slowing down and the force is in this direction, then the acceleration is in that direction, so it's a negative value. So we get the, oh, I'm sorry, I was solving for the wrong thing. Just ignore all this. I'm solving for delta x, so we would move it over. It's going to be v naught squared divided by 2a. That's delta x. So now I'd substitute in the acceleration. So it's going to be v naught squared over 2 times the coefficient of kinetic friction times g. That would be my change in position. There you go. So that's friction. Let's do an inclined plane problem. So suppose I have a block on a ramp, some angle theta, and it has static friction. So the coefficient of static friction, we'll say 0.6. And we want to know, like, how high can I raise this until it breaks free and starts moving. So again, the first thing we do is our force diagram. So you have the force of gravity, or the weight, which is always mg. And then you're going to have the normal force this way. And then you're going to have static friction working this way. And then I'm going to go ahead and draw my xy. So I'm going to do x is down the ramp and y is perpendicular to it. And now I'm going to go ahead and just add in my components right now. So this is fg in the x direction and fg in the y direction. And theta goes up here. So there's my force diagram. And now we're looking at, when does this thing start to break free? So the thing is that when it breaks free, at the moment that it's going to break free, it's still not moving. So there's no acceleration in the x and there's no acceleration in the y. So the acceleration in the x is 0 and the acceleration in the y is 0. That means the net force in the x is 0 and the net force in the y is also 0. So the net force in the x direction, we need to find all the x's. So we have this one and we have one down here. And we're calling down positive, so this would be fgx minus static friction is equal to 0. In the y direction, we have the normal force and the force of g in the y direction. So it would be the normal minus fg in the y direction is equal to 0. Now we're going to start substituting our values. So fg in the x, it's opposite the angle, so this is going to be fg sine theta. minus static friction is the coefficient of static friction times the normal force. That's equal to 0. So if I move this over, I would get the force of gravity sine theta is equal to the coefficient of static friction times the normal. But I don't know what the normal force is, so let's go over to the y. So if I move this over, I get FGY, and then we're going to have to use trig to get the FGY. It's next to the angle, so that's going to be FG cosine theta. Now I know the normal, so I'm going to substitute that in here. So we get FG sine theta is equal to the coefficient of static friction times FG cosine theta. Now I see I have a force of gravity on both sides, so that cancels. So I would just divide this over. So I get sine theta divided by cosine theta is equal to the coefficient of static friction. And sine over cosine is tangent. So I get tangent theta is the coefficient of static. And so theta is going to be arctan of the coefficient of static friction. So this would be the angle max. That's how high I could go before this thing broke free. So again, what I really want you to focus on is the physics. We set this up, and then just as we go start working down, we start substituting things that we know and rearranging it. So just when you approach a problem, you may not know right away how to solve it, but if you just start with the basics and then just start plugging away at it, a lot of times it just kind of takes care of itself. The last request, and I forgot about this, was to do a projectile motion. So let's say we launch something at an angle, theta, and some velocity. Now if it goes up and lands back where it started in the y direction, then we can answer all these different questions. How far did it go? How high did it go? How long was it in the air? And remember, for how far it goes, you have your range equation on your equation sheet, so you can use that. But what I'm going to do is I'm going to find, I'll find the time it takes. How long is it in the air? Because typically with a projectile, we're going to have to try to find that. And so over here on the velocity vector, I'm going to go ahead and draw in my velocity in the x and my velocity in the y. So this one is going to be v cosine theta, and vy would be v sine theta. I'll go ahead and write that in, because I may need that later. So constant velocity in the x direction and constant acceleration in the acceleration equals g, and it's down, and it's always down. So now we can use some kinematics. So I want to find the time it takes to go up and then back down. So what I'm going to do is I'm going to say, okay, well, it starts with an initial position and it ends with a final position, but they're both equal to 0. So now I can find the time it takes to hit the ground using a position function. So y equals y naught plus vy naught t plus 1/2 at squared. So my initial and final are both 0. My initial velocity is v sine theta, and that's times t, plus, but it's not plus, because my acceleration is down, so it's negative, minus 1/2 g t squared. All right, so this is 0. I get 0 is equal to, notice these both have a t, so I'm going to factor out one of the t's, equals v sine theta minus 1/2 g, and I factored one of the t's, so I got one left, times t. And now we break this up. So this piece, and then we're going to take this whole thing, and we set them both equal to 0. So v sine theta minus 1/2 gt equals 0, and then t equals 0. So this one right here, that's this time over here, t is equal to 0. That's not the one I want. I want the t over here. And that's in here. So we'll move this over. You get v sine theta equals 1/2 gt. So we're going to get 2v sine theta divided by g equals t. So that's the time that's in the air. And then once we have the time, now we can figure out all kinds of stuff. We could figure out, you know, how high did it go? So to go how high, we would take half the time, which would just be v sine theta over g. And then we just plug it in there. If we want to know how far, I could take that time and plug it into, you know, x is x naught plus vx naught t plus 1/2 at squared. But in the x, it's constant velocity, so we would just multiply vx naught by this value. And that's it. That's how we step through these. If you wanted to, you know, launch it and land up on a, like up here on a cliff, well, then you would have some other final position. So again, I'd probably, you know, if we knew how far away from the edge it was, we could figure out how long it takes to get that far. And then that would tell me the time, and then I would apply the time to the y. But basically, you're going to have to work with time, and you just work with a kinematic equation. That's just kind of how you step through these. So anyway, I hope that helps. That's all that I got requests for. So study, practice, do the quest, do the practice that's in the quest, and you should be good to go.